Good evening, everyone. My name is Jonathan Baker from PingCAP. I'm the Director of Developer Relations, and I am your host for this evening's meetup on Databricks on TiDB and TiDB on Cloud Disk. This evening, we have a couple of great presenters set up for you. We're going to be starting this evening with Min Zhou. Min Zhou is a staff software engineer at Databricks, and he'll be presenting on how Databricks is moving from MySQL to TiDB and the performance and tuning that they've been doing on that product. After that presentation this evening, we'll be working with Yi. Yi will be is a database engineer at PingCAP, and he'll be presenting on using TiDB on Cloud Disk, specifically with Amazon Web Services. A few notes about our presentation this evening. Our presenters will be presenting for about 20 minutes apiece, 20 to 25 minutes apiece. We will be doing Q&A at the end of each presentation. For all questions, please put your questions in the chat. We'll be reading the questions out of the chat here on the live stream and presenting them to the speakers so that they can answer your questions. And we'll do our best to get to every question that's out there. If we don't get to your question, please just come back to us later. We'd be happy to get back to you directly, or we'll post that information on our website after this is all over. At the end of this session, we will also be doing a survey just to see how your experience goes for the entire session. Thank you very much for attending, and we'll get started right away. So the first thing I'd like to do in this presentation is spend a few minutes just talking with you about TiDB, PingCAP's primary product here, and the reason we're having all these conversations. In order to understand this, I'm going to spend a couple minutes just talking to you about the evolution of data management, kind of talking a little bit about how TiDB works, just as a setup to the people who are talking after us. Most of their conversations are pretty technical. I'll spend a couple minutes just preparing you for what they're about to talk about. But the reason I always start off with this slide is because the data management space has worked a lot like the rest of computing technology over the last 50 to 60 years. If you look back from the days of monolithic mainframes where computers filled an entire room, going through the stages of having computers go to desktop machines, then from desktop machines to internet connected machines, to computer rooms, now from computer rooms to phones, to wearables and all the other things that are currently out there, you realize we've made enormous strides in the computing technology of the space during the last 50 years. We've also made a lot of strides in the interconnectivity of those systems. The internet itself was non-existent during the time of those monolithic mainframes and only started coming online in its nascent form in the 80s and 90s when we started seeing dial-up modems, and dial-up modems eventually getting replaced by wires, desktop machines being cabled directly into each other. If you think about it, it wasn't so long ago that we actually didn't have internet all the way from, say, from one house to another or from business to business. That evolution of the networking evolving into the cellular phone grid and even being available on airplanes is something very recent. So it's not surprising that data management has also evolved at that same time. We've gone through multiple different stages, primarily back and forth with a very simple concept called set theory. Set theory, of course, is the core of relational databases, the idea that information can be stored in sets that interrelate with each other. And that started off the RDBMS cycle many years ago, starting in 1976 and through the 80s and 90s. Then, of course, we moved to a point where we needed information to be faster, and we moved to a NoSQL concept, which was maybe we don't need this relational set at all. We can do it all with just keys and values. That made things a lot more efficient, but eliminating the sets themselves also took away some structure from organizations and had its own limitations. And so what you're looking at right now is kind of the evolution of those two things coming together. And TiDB really does show how those things can be brought together, and two different technologies can be brought together to basically solve a problem and get the best of both worlds. That we can have both a set theory related relational database system with a key value store underneath it, getting the best of being able to make queries using SQL, but also having the power of key value. If you think about it, and this is TiDB's detailed architecture, what we do is actually pretty complicated. The idea behind it is really a very simple one, right? Taking key value stores and being able to distribute them across multiple nodes in multiple different regions, and being able to keep copies of that information so that even if one goes down, another one will still be able to take its place. But in truth, there's actually a lot more pieces that go with it. Along with the key value stores that are out there holding that information, we also have a relational database translation system, TiDB, which takes the SQL queries and maps them up to the key value pairs to make sure that information is always available. We also now have Spark drivers that allow us to perform relational queries in a hybrid form in what's more like a column restore system. So if you think about it, the evolution of the database system we're using right now actually is a pretty complicated system that actually does hybridize both those things together. Obviously, the TiDB software that you're using, and you've been using for several years now, has started off with open source coming out of China. And it's been remarkably successful and has evolved very, very well. Along with that Chinese open source, what we often call the community version, we also now happen to have something called the TiDB Cloud. The TiDB Cloud offers all the benefits of the on-premise version that you're used to using from community, but in a managed cloud that we've been working on for quite a while. And the reason I talk about TiDB Cloud right now is to do a little bit of a promotional plug. We just released the Cloud Developer Edition, which allows every developer out there to get their own cloud edition of TiDB Cloud free for an entire year. So if you haven't taken a look for it, go sign up for it at TiDB Cloud. Anyway, that's enough of my introduction time. Let's get right to our presenters. I'd like to start off today with Min Zhou. He's the staff engineer at Databricks. He's going to talk about how the big data and AI company that's Databricks is starting to migrate over to TiDB. Min, take it away, please.
Let me share my screen.
Yep.
Hi, everyone, and thank you, Jonathan, for the introduction. This is Min from Databricks, and today I'm going to talk about the TiDB at Databricks. First thing first, let me, okay, so it doesn't work. Let me make an introduction of our company, Databricks. So Databricks is a big data and AI company, and we are created by the original creator of Spark. And right now we have so many open source projects like Delta Lake, ML Flow, blah, blah, those. And we're a global company with about 5,000 customers and also 450 plus partners. And our company runs Spark cluster in cloud, and also Databricks SQL is a data warehouse solution and also AI solution. And yep. And next is the MySQL at Databricks. Right now we use MySQL in many places. Majority of the MySQL data are the control plane data, service data. So we store our account data, Spark cluster data, Spark job data, as well as SQL history and SQL catalog data, and also the other data in MySQL. In terms of the scale, we have around 100 regions over 3 clouds across all over the world, including the AWS, Azure, and GCP. So in each of the region, we have multiple MySQL instances on that because of the scalability issue I will mention later for MySQL. Roughly, we have about 100 terabyte data on MySQL already. That's the data at MySQL at Databricks. We have been seeing many problems with MySQL. The majority of the problem is the scalability in terms of the storage and CPU memory and also the connections. So we can see like there's so many servers and they connect to MySQL and they're limited by the connection. And so we want to find alternatives that is horizontally scalable and highly available, and then strongly consistent, and also is fully compatible with MySQL. So after search around and a lot of research, we figured out TiDB is our answer. And today my session will cover 3 parts. We'll break down into 3 parts. The first part is infrastructure, discussing how do we deploy TiDB in our Kubernetes cluster, and then also how we maintain it. And the next part is the performance and how we tune TiDB on Kubernetes. And the last part is migration, how we migrate from MySQL to TiDB. Okay, that'll work. Okay. This is the challenge when we maintain TiDB. The first thing is when we use MySQL, we use cloud manager manage the MySQL, for example, AWS RDS or Azure MySQL. But right now we will maintain our TiDB ourselves. So we need to maintain the HADR ourselves. So it also will bring significant operational overhead to us. And also because TiDB is more scalable and then MySQL, we are considering consolidate all of the MySQL instance into one TiDB cluster on each region. So, but the sharing will also give us the penalty of isolate of the for example, there's a bad query, they can occupy all of the resource. So we need to think about the isolation as well. And also, because our services are deployed in Kubernetes, so we want to deploy the TiDB in our Kubernetes cluster as well. So those are the challenges we are facing when we deploy TiDB at Databricks. And this is our architecture. Because of some historical reason, we launched a dedicated Kubernetes cluster on the right side for TiDB only. And then our service, contributing service, will be on the left side. For example, the cluster manager, the jobs manager, and also the Spark SQL, Databricks SQL will be also maintained in contributing Kubernetes on the left side. It will send the SQL request to the right side. So between these two, we have a load balancer, and the load balancer has a service IP and service endpoint. So the SQL will flow into the right side of Kubernetes. And inside the Kubernetes cluster, we have one TiDB operator in each of the region. And this operator maintains multiple TiDB clusters. Each of the TiDB cluster will in one Kubernetes namespace. And inside the namespace, we have several TiDB components, which mentioned by Jonathan. So that's PD, TiDB, and TiKV. And also we maintain the TiCDC service for replication. I will mention it later for TiCDC. Okay, that will work. Next. And because we need to build a highly available TiDB, so we think about whether we can torrent the zonal disaster. So we built this zonal redundancy. And we will deploy each TiDB component in each of the zone. And then if one of the zone fail, and the other two can take care of it. In addition to the zonal redundancy, we also build a regional redundancy. So basically we have two choices. The first one is we can build on top of TiDB because TiDB support Raft consensus. We can make this strongly consistent. But downside for this is because we have several regions. Between this region, we can see like a very high latency, especially in Azure. They can take up to like 500 milliseconds per network package. And also, another choice is we can use the traditional way, use binary log. We probably see some like lags or inconsistency, but we can torrent that. And also the major reason we chose the binary log based one because we have some internal tool running against the MySQL. Which can replicate MySQL data from one region to another region, and they can pair together. So we have active replication between the MySQL. So we want this TiDB architecture also work with our existing system. So we choose the binary log based replication for regional redundancy. Yeah. In In addition to the HA improvement, we also ensure the durability. So we will do a daily backup using the TiDB tool called BR, and we will do it daily and typically 7 days. Okay. Regarding to the failover, there are many kind of failures. For example, the container failure, the pod failure in Kubernetes, and also we will rely on Kubernetes to bring it back. And also Kubernetes node failure because TiDB operator using stateful set for TiDB, and they cannot recover the stateful set after Kubernetes node failure. We have some internal tool to look into the liveness of the node and then do the recovery for the stateful set. And the remote disk failure, which is real and is handled by TiDB. And then if there is a network partition, and the TiDB will become unavailable, but it needs some human intervention. And also we will do operations, and the basic operation include like TiDB upgrade. We will rely on the TiDB operator, which will do the loading update. And also the Kubernetes node update. For example, we want to upgrade the Linux kernel, or we want to replace retire a node. And then we usually do a loading update. And the process is we will bring up a new node, and then we will tend the one of the existing node and migrate all of the pod into the new node. And after the new node is ready and TiDB component on that node is ready, and then we start another, and then we terminate the old one. We start a new process. And then this is the loading update for Kubernetes node. Okay. And then, as I mentioned, we need service isolation. We have two choices. The first one is we build up two-tier TiDB clusters, tier 0 and tier 1. And tier 0 is support the critical services. For example, the cluster manager, the jobs, and those stuff. And then tier 1 is a shared TiDB cluster, is larger, and the less critical one service will share the TiDB cluster. And in tier 0, each of the service will be equipped with one TiDB cluster exclusively. For example, the cluster manager have one dedicated TiDB cluster for it in tier 0, and the jobs has one tier 0 TiDB cluster in it. This will build a fully isolation, but the downside for this is, for example, if you have a query that cross the isolation, or there is a service which is currently in tier 1, they share with the others, but as the business grows, it might be promoted to tier 0 service, and then you need to because data is not sharing between the clusters, you need to do a full migration from the tier 1 to tier 0. And so the second solution is a placement tool, a placement rule built in TiDB. The basic idea of placement rule is inside the PD, the brain of the TiDB, you can control the data chunk and map into a data node, the mapping between them, and then you can pin a set of data, for example, a database data, to some sort of a group of the nodes, and then this data occupy the nodes exclusively, but physically they are isolated. with the data set, but logically they are still in the same TiDB cluster. So data sharing or query across data set, you can still work. But right now, the placement rule is still in development. And right now, we cannot use SQL to define the rule or some limited SQL to define the rule. So it's still in development. It's not that mature. We're working with PingCAP to see whether we can test it in Q1 next year. Yeah, we're looking forward to it. Okay, next part is the performance tuning. Okay, so this is our initial setup in Azure. We have a bunch of TiDB nodes, a TiDB pod, and a bunch of PD pod and TiKV. Each of the TiKV pod is backed by 2 terabyte storage, and also we will use System Bench to benchmark it. The workload is picked up from our internal SQL history service, and we use System Bench to simulate the traffic, but with very high concurrency and with very high traffic, like 10x time than our regular traffic. The first thing we figured out is we want to figure out is whether we want to use local NVMe disk or remote disk. After our benchmark, we can see the local NVMe has better performance, but it will give up a lot of operational overhead because it's local. If we want to terminate one instance or one node, we need to firstly copy of the data, the entire node's data, and migrate from one node to another node. But to terminate a node is usually not under our control in cloud because the cloud provider might retire some of the data, ton of the nodes, and then usually they are not terminate one of the nodes. They will terminate many of them, right? And then you will lose the 2 copies of them. You will lose the consensus. So there's no choice for the local NVMe in cloud. So we decided to use remote disk. But remote disk has, although it has less operational overhead, we can like detach the disk before the retirement, and then we can reattach to another new node. But it has poor performance, especially in Azure. Okay, and at the beginning we get this number 4K TPS 682 millisecond, but make a declaration. We are run it on Azure. AWS EBS is much better, and also we are running very high workloads. So regular workloads are much better. And also this is write intensive. The reading, because most of the reading is read from memory. So the read is very good. It's like much better than MySQL. And then if you are on regular workload, the write performance is slightly slower than MySQL, but this is very high traffic. And we can see this number. 682 milliseconds, that's very long time. And then we look into the Azure portal, the website. So we can see the remote disk typically take about 1 millisecond per disk write. But why is it reflect into the end-to-end query latency to 682 milliseconds? So we will try to answer this, and we try to figure out what happened inside. And then we look into the TiDB write path. So you can see, I will take a brief introduction for this write path, and Yi will introduce more about, dive deeper into this. So when the query comes into TiDB, it will served by the TiDB server on the left side. This is a stateless query engine for TiDB. And the query will be powered by a SQL layer and then come to the phase committer layer and then we'll send to TiDB. And inside of TiDB, you can see from the right side, there are a bunch of worker group, schedule worker and a storage worker, and between the worker there are some queues, and then the storage worker will write data into two places. The first place is the ref log. The ref log and the real data will be right into the KV storage. And both of them are backed by RocksDB. So on the left side, the ref log is right in RocksDB, and also the KV side is also right into RocksDB. Okay, and the first thing we can think about is because we are writing to the same storage, and the RefDB and the KVDB are sharing the same disk. Whether we can separate them to get a better performance, yes. And then we do a separation. We create a dedicated remote disk for the RefDB. That's because the ref log is very small. We just need 64 gigabytes storage, and then still keep the 2 terabyte for the KV storage. Then we can see, and also we did some other configuration optimization, for example, the bound, the slope, and TCB tuning. And after that, we can see 7.8 TPS and 451 millisecond for our workloads. So that's nearly double the TPS, the throughput, and around 30%, 33% improvement on the latency. But still, it's not enough. And then because 450 milliseconds is still a very long time. Then we look into the metrics provided by TiDB. So one thing we noticed that is the scheduler queue. As I mentioned, in the TiDB layer, there are a bunch of worker groups, and between the worker group, there are some queues. So we can see these 3 TiDB pods, each of them have in average 1,000 operations executing. And then we look into the I/O, the other stuff. We can see the I/O is slow, but how it reflects to the end-to-end latency, 451 milliseconds. And then we come up with a hypothesis. The hypothesis is because of the lower layer disk I/O, it's very slow, and then all the requests is like queuing up in this queue, and then you can see from the end-to-end query latency become very slow because of their queuing. And in order to confirm that, we take a look at the low layer, and then we did some profiling. And then one thing we did is we use I/O top, and then from the I/O top we observed that there's at a time there's only one single thread is working on this I/O, and then we did a perf profiling, and we can get this result. We figured out almost all of the latency is coming from the disk layer. These 2 parts, you can see on the right side, that's because of the ref log. They need to flush the data, the ref log, into disk. So there's a wall F data sync. And because of this wall, it also triggered the left side, the file system journal log for the wall. So both of them are single threaded, and they are serialized. So each of all the other requests queued up. So we want to find a solution for it. The first workaround we can think about is whether we can do it very quick in the short time and from the hardware. So whether we can parallelize these wall logs. So the first idea is we can use a smaller instance and smaller storage. For example, in this case, we launch 6 TiDB pod, but each TiDB pod is with half memory, half CPU, and half the storage. For example, we allocate 1 terabyte for each of the TiDB pod. Then we can get a very good performance. That's around 13K TPS and 314 milliseconds. That's another roughly double of the TPS and another like 30% improvement on the latency. Yeah, I think because hardware is easier, but I think we have another idea that from the software. Because right now, in each of the nodes, we have only 1 RocksDB, 2 RocksDB instance, 1 RocksDB instance for all of the data's wrapped log. Whether we can create multiple of them, for example, 4 of them or 16 of them to parallelize the wrapped logs, because and then we can parallelize the disk write. Right. But this, if we do this, it will modify the TiDB code, and then also it will cause some compatibility issue with the old TiDB version, because it will change the data format in the disk layer. This is our prediction. So we predict that we can get this number, this latency. Okay. The last part is migration. The migration is we use the replica based. The migration we have 2 stages. The first stage is pre-checks. So we will make sure TiDB will work exactly the same as MySQL. So we will change our unit test, the MySQL unit test, and then be backed by TiDB. We run all of the MySQL tests against the TiDB to see whether it has a compatibility issue or not. We've been seeing some, but we have some workaround. And also we will launch we have some internal tool that can launch all of our control plane service in one Kubernetes cluster and for testing, and that backed by MySQL. And then we can change it into TiDB and then run the same integration test against TiDB to see if it behaves the same as MySQL or not. In addition to that, we add an interceptor layer, a wrapper, to our data access layer. That's the data source on the right side. You can see from the diagram. We add an interceptor. This interceptor will replay the traffic, the SQL traffic, and then write to in Kafka. And then we will create a dev MySQL and also will dev TiDB for testing. And for testing purpose, we can compare the two. And we will launch a consumer which will replay the TiDB traffic and then write into and read from MySQL and TiDB. And also we use the TiDB tool to compare the data between the test MySQL and test TiDB. So after done those pre-checks, we will move to the actual migration. The migration is replica based, as I mentioned. We will use TiDB built-in tool. It's called DM, and that's for data migration, which can help you to do an initial dump and the incremental replication from MySQL to TiDB. And then after TiDB is a catch up, and then we did some necessary checks. We will do the cutover. We will cut over the MySQL client from pointing to the MySQL to TiDB. And then at that time, we will also do a in-reverse replication, because from TiDB to MySQL, we will use TiCDC here to do the in-reverse replication. That's for the case of rollback. if everything, like if the after migration, everything, something is messed up. So we will still have a replication from TiDB to MySQL, and then we can fall back to MySQL after migrations. Okay, that's all of my talk. Okay, any questions, feedback?
Thank you, Min. That's been great so far. Yeah, really appreciate that. We do have a couple questions from the audience. Let me just get to them right here. Lost my Zoom. There we are. Okay, so let me ask you the first question that came from the audience. Manish asked, are the 2 terabyte and 1 terabyte storage shown, are they single cloud disks?
Yes, they are single cloud disks. So we will have, we will use the persistent volume. This will launch 1 terabyte each, and then each of the 1 terabyte remote disk will be attached to the instance.
Okay, great.
And also the instance only run 1 pod exclusively for the performance.
Okay. And he also asked, what kind of a file system are you using?
Is it again? Cloud system?
What kind of a file? Are you using any type of file system underneath this,
we
or
use
is it all raw?
EXT4. Right now we use EXT4.
EXP, okay.
Yeah.
Great. Rui asked, is RocksDB a performance bottleneck in practice?
In practice, in regular workload, RocksDB is not. But if you have very high traffic, especially on writing traffic, for example, you have like 800 concurrent writing to the TiDB, you will see the Raft is the bottleneck.
I see. So did you get just to follow up that question, did you find that RocksDB was that there were write performance issues when you had them both shared? Is that why you separated them?
We still see very high like this I/O from the ref log compared to the KV, because the KV you can store it in memory first, and then flash if the memory is full, like every 32, I don't know the number, let's say every 32 megabytes, I take a flash. But ref log, you need to sync it every time because it will keep the consensus for you. So that part of IOPS from the ref log is very high. Although the storage is very small for the ref log, but the IOPS is very high.
Yeah. Okay, so Andrew Wang asked, did you run into any issues setting up your MySQL to TiDB or TiDB to MySQL replication? Yeah,
because we're using Flyway, and Flyway have a lot of schema migrations. And for example, we used to do some like incompatible schema migration. For example, I delete the primary key and then I add another primary key. That is not supported well by TiDB. And also, if your query has some stored function or triggers, that's not supported by TiDB. And another thing I want to mention is a foreign key constraint. It's not supported well by TiDB right now. But right now we don't need it because we don't have those foreign key constraint.
Okay. I have time. I apologize. We can't get to all the questions we have out there. I have time for one more question. Huxon asked one rather technical question, but I like it. Does the write transaction wait until all the bin logs applied on the remote replica, or just until bin log materialized on the remote replica?
That part I think I can ask the TiDB PingCAP.
Okay.
That's the Raft, how the Raft works. So
yeah. Sounds like something we'll ask.
I can answer, but I don't think I don't know whether I can answer.
That's okay. Or not. Well, that's good. That's a really good point. We'll have the TiDB. I'll ask the TiDB engineers to get back to posting those questions later.
Yeah.
Okay. So, ladies and gentlemen, thank you so much and Min, thank you very much for your presentation. That was excellent for Databricks.
Thank you, Jonathan.
Yep. Thank you very much. Yep. And we are now going to move on to the next presentation for the evening. This presentation is by Yi. He is an engineer at PingCAP, and he will be presenting on the topic that is using cloud disks. Specifically, he's using cloud disks on Amazon Web Services. Yi, are you there?
Yes, I'm here.
Great. Okay. Looks like you're ready to go. Go ahead.
Cool. Thanks, Jonathan. Yeah. This is Yi from PingCAP. I'm on the TiKV storage team. Today, I'm going to share about running TiDB on the cloud disk or in AWS, the EBS service. And for our TiDB cloud service, which we provide TiDB as a service to our users, we are switching from using local disk to cloud disk, which is the EBS. And for our on-premise users who deploy TiDB on the cloud, we are also recommending them to use the cloud disk. And today I'm going to share why we prefer a cloud disk over local disk, and what the performance would be like when running TiDB on EBS, and also what are the optimizations that we have done to improve the TiDB's performance on EBS. So before digging into EBS, I would like to talk more about TiDB itself, because the reason why we prefer EBS over local disk is more TiDB specific. Yeah. So this shows an overall picture of TiDB cluster. TiDB is a distributed database, which is MySQL compatible, and it has several components inside a class inside TiDB cluster. So there is a TiDB component which handles the SQL processing and being the compute node in the cluster, and there is PD, which provides the metadata service and also provides TSO service and so on and so forth, and it also controls the load balancing for TiKV. And then we have TiKV, which provides a distributed key value service, and being the storage node in the cluster, mostly handling the transaction type of queries. And to handle analytical type of queries, we can also add the TiFlash node, which have a columnar store, which is better at handling the analytical type of queries. But for today, we'll just focus on TiKV. So for TiKV, it provides a distributed key value service. And for the full key range, it is split into small ranges. We call them regions, and each region is the unit of replication and load balancing. And normally, with each region will have 3 replicas, and those replicas will be distributed among all the TiDB nodes. And all these replicas will, for one region, will form a rough group. And so because for one region there will not be 2 replicas located on one single TiDB node. So whenever we lose one TiDB node, for all the regions on this node, there will still be 2 replicas located on the other live TiDB nodes. So in this way, those replicas can still provide serve traffic. So in this way, TiKV provide a high availability. So this is about losing one TiKV node. But how about if we lose 2 TiKV nodes simultaneously? Yeah. So here is an example showing what happens if we lose 2 TiKV nodes simultaneously. So here we have 4 TiKV nodes in this cluster, and we have the node 1 and node 4 go down simultaneously. And there will be some regions that have 2 replicas located on both of these down TiKV nodes. For example, here we have region 1, region 4, and region 5. Both have all of them have 2 regions. Two replicas on these two down TiKV nodes. As a result, those regions will lose the majority of the replicas. And by design, because we are using RAW, the consensus protocol, losing majority means that those regions, those part of data are unavailable. And what's more, in this scenario, the cluster wouldn't be able to recover themselves, and it needs human intervention to bring the cluster back up. So yeah, so here is the problem. So by design, because we are using consensus protocol for replication, when we're losing majority of the replica, and then it will lead to unavailable to some part of the data. And in TiKV, because of the constant load balancing, we are running the regions are mostly randomly scattered on different TiKV nodes. And so when we lose two TiKV nodes simultaneously, there is a high probability that there are some regions that have two replicas located on these two failing TiKV nodes, and which will cause unavailable for some part of the data. And that's the problem. And of course, we could consider to use a technique called copy set, which will allow us to cleverly place those regions on the TiKV nodes, so that when we have two failing TiKV nodes, there will be a lower chance that it causes unavailability. But on the cloud, there are another similar problem that even with copy set, it couldn't be solved. So on the cloud, we usually will deploy across three availability zones, or AZs, and so and also by using a feature in TiDB called a placement rule, we could place all the replicas of the region across different availability zones. So even when one AZ completely go down, for all the regions, we still have two replicas located on the other availability zones, and as such, they can keep serving traffic. But what if, along with one AZ down, we have another node in another AZ goes down? So in this example, we are showing that the AZ1 is down, but the node 3, TiKV node 3 on AZ2 is also down. In this case, we have the region 1 and region 3 have the majority goes out, and it couldn't serve traffic. And we call this type of problem AZ plus 1 failure. And in this case, we still have we're still left with the cluster that is unavailable and needs human intervention to bring the cluster back up. You may think that this type of failure may happen really rare. How come when there is a whole AZ goes down and there is more machines go down? But we actually we actually saw one in production, and because that production cluster is really big, and it takes a really long time for us to and a lot of human effort to bring this cluster back up, and it was really bad. So we want to solve this problem, and so that's why that's where the cloud or EBS come into the picture. So EBS stands for Elastic Block Store, which is the cloud disk on AWS. It behaves just like a normal block device or disk, and EBS volume can attach to one EC2 instance as a disk. But it has a nice feature that the data are persistent, independent to the EC2 instance, which means that when the EC2 instance fails, the data stored on the corresponding EBS volume is still there, and we can easily remount this EBS volume to a new EC2 instance, and the data is not lost. And under the hood, so EBS have, I believe, 2 replicas within an AZ, so it have a higher availability compared to lower failure rate compared to EC2 instance. So comparing using local disk and EBS, so when we are using local disk to store our data on EC2, when one EC2 instance fails, the data stored on the node are also lost. And so in this case, TiKV will need to re-replicate the losing replicas in the background. And it takes time and the CPU and IO resources. And if before the re-replication is done, there is another EC2 instance fail, then it will lead to unavailability. It will lead to unavailable because of the issues that we just described. With EC2 with EBS, the EBS failure happen far less often, and when one EC2 instance fail, the data in the EBS volume is still there, and with the help of Kubernetes, we can automatically remount this EBS volume to a new EC2 instance, and the data will immediately show up again, and so we don't even need to re-replicate those data, and it avoids the unavailable issue that we just described. So with EBS we can mitigate the issue that the unavailable issue, for example the AZ+1 issue. But how about the performance? Yeah. So to figure this out, we run some simple FIO tests on the EBS volumes, and we want to compare the performance between EBS and the local disk, and also there are several different volume types that EBS provides, namely GP2, GP3, IO1, IO2, and those different EBS volume types provide different performance characteristics, and also they come with different pricing. So we want to have some benchmark to figure out which type of EBS volume we want to use. So here we are showing a single thread FIO test with 4K IO and fixed 1000 IOPS, and here we want to see the latency across different disk types, and here we can see compared to all the EBS volume types, the local disk outperform them in terms of latency by several times. And here is another benchmark with multiple threads, again with 4K IO size and 3000 IOPS in total, and the local disk is outperform all the EBS volume types by several times in terms of latency. So but looking at this benchmark, you may think that the EBS performs poorly, and if we run TiDB on EBS, we will end up with very poor performance. There is another set of benchmark we run that shows a slightly different story. So we construct the FIO test so that it will simulate a mixed workload that simulates what TiKV does, and it will have several threads doing small writes and several threads doing small reads, and there will be some threads doing large writes to simulate the compaction. And so with this benchmark, we'll see that as we have a mix of workload, and especially when we have more intense workload against the disk, the latency gap between EBS and the local disk actually becomes smaller. And here you can see that on the rightmost side, the latency difference between EBS volumes and local disk is less than 2x. So it shows that when we have a moderate workload on TiDB or TiKV, then the performance gap between using EBS and using local disk will not be that much. Yeah. So we continue to run some actual benchmarks on TiDB, and again here we are using the TPCC benchmark, and we run run it against TiDB, and when TiDB is running on different EBS volume types, and we compare to the TiDB that using local disk, and we use we test TPCC with different number of threads to simulate different type of workload, and so with a smaller number of threads which simulates lighter workload, we actually see in some case the local disk indeed still have advantage, especially when compared to the GB3 volume type that we plan to use. When using local disk, it still have a lower latency. But when we have a heavier workload, for example, when we have 200 or 800 threads, TPCC client threads, the EBS actually perform better. The reason is that TiDB is CPU bounded in this benchmark, and actually under many other type of workloads, and so the disk latency will represent a smaller ratio of the overall performance, and because they're on AWS, there are more EC2 instance type that support EBS than the with local disk. We only have the I3 or the C5 instance type that to choose from, and those instance types have a less powerful CPU. And so with EBS, we could choose to use more instance type with a more powerful CPU, and so to achieve a better performance. So as a result, with some workloads, when with using EBS, we actually can achieve better performance, and the performance disadvantage when the workload is lighter. That's the trade-off we are willing to make. And so we switch from using local disk to use EBS, and over time we have more and more users that using the cloud disk, and we are gaining more experience with the EBS, and we notice there are some optimizations that we can do to improve the performance when running TiDB on EBS. The first thing is that since we are using RocksDB as the storage engine in TiKV, RocksDB will run the compaction in the background, and the compaction is when the compaction kicks in, it usually is up a lot of I/O throughput. And with EBS, the I/O throughput is limited, and then we for us we usually use EBS volume with several hundred megabyte per second throughput limit. And when those compaction kicks in and it stops the I/O throughput, it will hurt the foreground I/O latency. So as a result, we work on two optimization to mitigate the problem. So one is the improved RocksDB compaction rate limiter, which will monitor the history of flush and compaction I/O that we have, and use that to smooth the I/O for the background compaction. And right, so by doing so, we will make the compaction runs instead of having a spiky compaction, we'll make it more run more smooth, and reduce its impact on the foreground I/O. And yeah, and another thing we do is we add the overall TiKV I/O rate limiter, which monitors all the I/Os, including the background I/O, the compaction I/O, and the foreground I/O that we are doing read and write, and also all the I/O that we issue for load balancing or backup, etc. And so and we assign priority to those IOs, and so if we are hitting the EBS throughput limit, we'll throttle the background IO and make room for the foreground IO. And with the help of these two optimizations, and as we can see from the picture on the right, when we have the relinter enabled, the write throughput becomes much more stable. On the right, that's without a relinter, and you can see that the write throughput become very unstable, very spiky. So this is for the IO relinter. And another thing we notice for EBS is that over time it can have performance jitter, and that's because under the hood it may have some failure, and sometimes it need to re-replicate data, and sometimes there will be network congestions, and that have all happened behind the scene, but it will shows up in for us as a performance downgrade for some of the EBS volumes, and sometimes especially when we have a larger cluster, we'll notice this phenomenon more often, and usually it might just affect one TiDB node at a time, but sometimes for some of the use cases we have, such kind of performance downgrade can have a cluster-wide impact. For example, for one scenario where we have a data replication scenario running in the upstream, and where this replication will apply the change from upstream sequentially, and below is spread evenly on all the TiDB nodes. When the EBS volume on one of the TiDB nodes become very slow, and this TiDB node also become very slow, this single slow node become the bottleneck of the whole cluster, and in combined with other issues we have, it in this case it actually bring the TiDB QPS down to almost zero. And so to mitigate this issue, we introduced a mechanism called slow node eviction. And the idea is that TiDB will periodically send itself a sample request to measure its own performance and report the result to PD. And PD will collect those samples and compute a score to decide if a TiDB node becomes slow. And if that's the case, then PD will trigger an evict leader scheduler on the slow node to basically remove it from the cluster. And so yeah, here are some pictures. On the top is a screenshot we take from the metrics on one of our production cluster, and you can see for this node the EBS volume becomes slower than normal for about 2 hours, and yeah, and it causes problem. And in the bottom it shows a simulation of the slow node eviction mechanism, and in here we are showing that when we start the simulation, we will simulate we should simulate the case where one TiDB node become extremely slow, and you can see here the overall QPS of the cluster drops. And then after a few minutes, the slow eviction kicks in, and it brings the QPS back up to normal. Yeah. So yeah, and so that's the two major optimizations that we have done on TiDB to make TiDB run better when using the cloud-based EBS. And there are actually some ongoing projects we hope to get done soon. And so one thing is the ROC engine. So for now, for each of the TiDB nodes, we have two ROCDB instances, one to store the ROC log and one to store the data. And for for the one that's so rough law, we actually see the background compaction kicks in often, and it consumes a lot of IO throughput. And as I have mentioned, the EBS usually have a low throughput limit. So we want to reduce the overall IO throughput consumption by TiKV. So we are replacing this RocksDB instance with a custom built rough log storage called Rough Engine, and it instead of storing the rough log as key value pairs in RocksDB, we now with Rough Engine we now store the rough log in log files, and with a custom GC routine that is more efficient than the RocksDB compression, we actually see in some of the benchmark, we reduce the overall TiKV throughput by 40%, which is a lot. Yeah, we hope to have the Rough Engine getting into the GA status in the next release, but which it means in a few months. And another bigger changes that we are making is the multi RocksDB changes. So for now, for the data on the TiKV node, we have one single RocksDB instance to store the data. And with the multi RocksDB design, we are changing to use one RocksDB instance to store the data for one region or the key sub-key ranges for TiKV, and essentially sharding this single RocksDB instance. And by doing so, we will greatly reduce the write application by this single gigantic RocksDB, and which will also help to reduce the overall TiKV IO throughput consumption. And it also has other benefits like it will enable us to do a physical snapshot when we try to run load balance and then move one region to another TiKV node. And it also because we reduce the size of RocksDB, we will reduce the global mutex contention in RocksDB. Yeah, and for this project, we hope we can get it done by next year. And so yeah, that's all I want to share today. Yeah. Feel free if you have any question. Yeah.
Yep. Thank you very much. That was an excellent presentation. We really appreciate it. We do have a bunch of questions that came into the chat while you were talking, and so we'll run through them really quickly. The first one that came in is, did you find any specific EBS storage type, GB2, 3, IO1, or IO2, was better than any of the other ones, or did they all have similar performance?
They do have different performance characteristics. For example, the IO2 or someone mentioned in the chat, the IO2 block express, of course have the best performance, but is more costly, and we incline to use the the cheaper GP2 or GP3 in the volume types, and for the GP2 volume types under a smaller workload, it will have a lower latency, but it will have a higher tail latency when we have a more intense workload. And also it has a limited IO throughput of 250 megabytes per second, which is not configurable, which we consider is bad. And for the GP3 volume types, and they tend to have a more stable latency, despite the latency when you only have very light workload, the latency will be higher compared to GP2, but it comes with a configurable IO bandwidth. So we end up using the GP3 volume types. Yeah.
Okay. And to follow up that, actually, Chris asked the question, so are there any plans to test the EBS IO2 block express that Amazon has just recently released?
Right. So yeah. So we are aware of the IO2 block express type, and we are excited about it. But right now the IO2 block express is only limited to the R5B EC2 instance type, and that instance type, per our experience, is low in stock. So sometimes we when we creating a cluster, we don't have we won't have enough R5B instance available for us to create a cluster. So it's not super practical right now, but well, we do feel the IO2 block express very exciting to try.
Yeah, I'm not surprised about R5B being not as available as the rest until they expand it. Okay, so Andrew asked this question. Databricks separated WoW and data disks, the WoW and the data disks for better performance. Did you benchmark the two separately, or did you benchmark them together?
For the benchmark, I'm showing we are having the write hello and the data store on the same one single disk. We do have benchmark that to see what if we have two EBS volume, one having the write hello, one having the data, and we on AWS EBS we actually see around 10% of throughput improvement, and then some and a slightly more stable tail latency when we are having such a setup. But so that's because the EBS have okay-ish performance compared to the Azure cloud disk. So we are not seeing that much performance difference compared to when we have Azure like in the Databricks case.
Yeah, sure. Yeah, okay. That makes some sense. So the next question actually come from Hanu. He said he is a little confused by why R5B with local disk would be bad in performance and R5B with EBS. Could you explain the difference between the two? Why the EBS is better? Why? Can you basically just clarify that a little bit?
Actually, with R5B, it doesn't provide local disk. So here the comparison is between using R5B plus. Here is using R5B plus EBS compared to using I3 with local disk. So the I3 have a less powerful CPU. And in this benchmark, the TiDB is CPU bounded. So as a result, with the R5B plus EBS, we have better throughput.
Sure. Okay. Yeah, I'm gonna just skip around a little bit here. I'm gonna go to Andrew Wang, who asked. So you had a section where you talked about the failures with the with where TiDB is running on a node, and all of a sudden that node would start to freeze up. He asked, how does the TiDB handle gray failures? For example, a node that intermittently is slow or is slow only for a few minutes at a time. Does the system that you set up also deal with that as well, or would it be able to find those?
Yeah. So yeah, as you can see, so the the only mechanism we currently have to battle the gray failure just this slow node eviction mechanism. And as you can see from this picture, it takes a few minutes to kick in because we want to avoid the false positive. So if there is a gray failure lasting for just a few minutes, this mechanism wouldn't be able to help.
Sure. Okay. And then a couple more questions have come in. The first one is from Pen Zhang. Have you benchmarked the block storage services from any other clouds, or was this just specifically done on Amazon?
We also did some benchmark on against, for example, the cloud is on GCP and also on Google Cloud, and also the cloud is provided by Azure, and we see that the EBS on AWS EBS actually provides the best performance, and also when say, for example, it's when it says that you are having a EBS volume with say 300 megabytes per second throughput, it do provide you 300 megabytes per second throughput. And with the cloudies for Azure and GCP and we can achieve the throughut claim by the cloud vendor. So and the performance is of those GCP and Azure cloudies are much less stable than EBS. Yeah, but still we have fewer experience with GCP and Azure, so yeah, we still need more work to figure out. Yeah.
Sure. Yeah. So my last question. And I have one question that came from Rui. I think he asked this question in context while you were in the middle of talking through a slide. And he asked this question that since TiKV is CPU bounded in this case, it seems like using EPS performs better is partly because more resources are available from EBS. I think that you were talking about that at one point about TiKV being CPU bounded. Can you just can you talk about whether EBS performs better because there are more resources available? So I think the question is actually it's a little confusing. I think what he was basically saying is that I think if I translate that question, this particular slide you talked about it being CPU bound in this benchmark, right? And then EBS provided better performance. You said that in your slides. I think he was asking like, so would it be why is EBS providing better performance there when you're CPU bounded? Could you basically just kind of explain that a little bit more?
Right. Yeah. So yes. By saying the CPU is bounded in this case, of course, the I/O is not bounded. So we are not hitting, for example, the throughput limit, the I/O-PS limit of the corresponding EBS volume we are using. So in this case, the EBS volumes still have good enough performance. Okay. Although the latency may be slightly higher compared to the I/O on the local disk then, but that's not the bottleneck. So yeah.
Okay. We have time for one more question, and we did get one from Ashwini. The questions are starting to get better. They're beginning to get a little bit more. They're wider, more divergent, and this one, of course, is about talks about cold storage instead of using. It's kind of the opposite of performance tuning. This is about cost savings. But they actually asked if there were any benchmarks or any information on using cold storage like S3 to take cold data or to take some of the data basically off of out of TiKV, especially the data that doesn't change, and moving it to S3 to lower the storage cost. If you guys have considered that, or have you done any benchmarks on it at all? Or
we actually consider using S3, but so that would be a larger architectural changes for us, and also there are different performance characteristics for S3. For example, if you just want to do a small I/O on the S3, then it's of course less efficient and more costly because it's charged by IOPS by the number of queries but we do considering some architectural changes that allow us to use S3. Okay. Yep.
Great. Well, yep. Yi, thank you very much for your time. That has been excellent. I think that's the end of all of our questions for this evening. So, yep. Thank you very much again. That was a very excellent presentation. So,
cool. Thanks, Jonathan.
So, ladies and gentlemen, just a few things to wrap up as we finish this evening. First of all, thank you again to Min and to Yi for the great presentations this evening. If you have any further questions, please feel free to send them to us. And actually, I actually put my email address in the chat. You can email them to me directly, and I'll make sure they get routed to the right people. We did want to tell you a little bit more about us. If you would like to find out more information about PingCAP, you can find out more, of course, at our website at pingcap.com. We also have a very vibrant community, both for open source contributors and for all of the customers that we have out there on Slack, tidbcommunity.slack.com. That channel is monitored pretty much all the time. There's about 50, 60 channels there with constant ongoing material. By the way, PingCAP is a global organization with our offices in China. We also have locations in North America, which is where I'm based, Japan, Singapore, and EMEA right now. We have over 550 employees operating in those 9 countries with a US HQ in San Mateo, California. And we just wanted to point out that we are, except I missed that slide. We are actually we're constantly expanding right now. We're definitely growing PingCAP on a regular basis. We're looking for people constantly in business, in community and marketing, which would be great. We'd love to have you on this side. For technical people, especially our product, and for all of our corporate functions, please take a look at our careers if you're interested in finding out more about PingCAP or potentially would like to be interested in a career here. Anyway, thank you very much for attending our presentation this evening. It's been great to have you all, and have a good evening or day.